Okay? Now, this is from 3, then I call this from 3. Look, from 3 I can equate YQ and XP. Okay? This is from equation 3. I can write here easily. Okay? Then thus from 2 here, okay, I can write YQR is equal, this over here is just, don't forget that, XR. You see, this is equal to, don't forget that, is X. X, and this over here is XY. See? So, I finished this, okay? Now, I'll move to G is equal theta. It's a function. Okay, here, G is a function, okay? Now, again, as I did here, okay, this is a pullback. In this case, is a pullback of theta. Don't forget that theta belongs to the polar coordinates. According to adjoint operator, I'm bringing from the polar coordinate to Cartesian coordinate. You see? So again, the same, is analogous what I did here, I will do for theta. So I derive, don't forget that theta is the inverse tangent of y over x. Okay? Just take the derivative of the tangent. So partial of theta with respect to x is just x divided by r. Okay? This is square root. Attention now. This here is x divided by r squared. See, because r is square root, r squared is just x squared plus y squared. On the other side of the adjoint operator, on the other side of the identity, xp of theta, again, I'm using this property. You see, x set of theta is just d. Don't forget that d is just x theta. You see? This is important property I call 4. So YQ now, the pullback, this case, the pullback, I will bring this, attention now, to the right-hand side. You see, that's easy. Now, I'll substitute, again, this derivative here and this derivative here. I just substitute over here, you see? So that's why I get this derivative here. You see, again, I substitute, okay, this partial derivative here by minus y of x squared plus y squared. You see, it's x divided, and partial of that with respect to r in this case. Okay? This is with respect to y. Quite easy. So this over here is the property which I wrote there. So y, now the pullback, okay, is y of theta, which is, don't forget, this component is x. This component is x, y. See? So YQ of theta is equal to this right-hand side over here, okay, which is XP of theta, which is equal to dr, which this is d theta. You see, d is x theta, the component. Now, the final formula, you see, I know that A is x, B is x, y. So xp, xr, x theta, this is a vector, okay? This vector here belongs to R2. This is a polar, okay, polar system. And xr is C, as I said, as I showed here. In this case, x theta is D, just see here. So xp is the sum I add, and this leads to this relation over here. So it's quite easy. So then I'll put a red mark here. You see how it's easy to see it. So this is a component, and this over here, it is another component, okay? So I showed here a very simple numerical example. You see, x is equal to square root of 3, y is equal 1. The component, I know, attention now, I have to have the data from the Cartesian, okay? That's my intention, is this, to transform the Cartesian to polar, which exactly what's written over here. I know, I have to know, I have the data just to calculate this component and this component, and then to obtain xp, which is the push forward from yq. This is my unknown. Numerical, as I said, xx equals 6, xy is equal 4. I just compute r and r squared. Attend, this is r and this is r squared. So it's just a simple calculus. So r squared is 4, r is 2. See? And in this case, xr, I just easily, I substitute right over here. See? Don't forget, this over here is xr. This x theta, okay? Which from this input data I can obtain xr and x theta. So the push forward of the vector yq, given the vector yq, is just this solution here. So that's it. Please, again, don't forget to put comments, okay? Positive or negative, but comment, please, okay? That's it.